What's that? Yeah, go to a different bag. Right? Like, okay. Today, guys, we are going to knock out, and I know we spent a bit of time, but I think we're going to be okay to do it. We are looking at 2.7, and our focus in our last section of Chapter 2 is on this idea of nonlinear inequalities. This is the first time we've really seen them. I shorthand constantly. Inequa is my shorthand for inequalities, just so you guys are aware. Okay. As we look at this, the first section that I want to kind of make here is we're just going to talk about polynomial inequalities. And that's kind of what we've already started with. And then we'll just extend this a skosh. So polynomial inequalities. And I will write it this one time. Okay. What this eventually boils down to, and we're going to keep relying on that statement that I made you guys tell me a second ago, and you're going to tell me right now. Functions can change from positive to negative in like two places. Really, there's three, but let's just say two. One of them is the what, JV? The roots, and Mickey, the other one. Of asymptotes. Awesome. Okay. Now, polynomials, just regular polynomials, don't have asymptotes because these are not rational functions. This is just one numerator, no denominator in these ones. Okay. As we're solving these, we can look at, and I'm just going to use an example for this. And we'll do a different one. Let's say we had x squared plus 3x minus, no, we'll just say is greater than or equal to minus 2. This is hard to think about. And the reason it's hard to think about is because we don't have a math notation or even a conceptual understanding necessarily of what it means to be greater than or equal to negative 2. I understand what it means, but we don't have a way to solve this because when we think about factoring and stuff, we're solving the zero product property. There's no such thing as a negative 2 product property. Okay, everything is always 0 when we deal with it, right? This is hard to think about. However, with one little change, we can make this so much easier. We can change, and I'm going to move this underneath. I'll just say ugly, which maybe it's not super ugly, but we can move it a little bit. Whatever I do to one side of an equation or an inequality, as long as I do it to both, as long as it's not dividing by 0, we're good. What would you suggest I add to this? So if I add a plus 2 to this, this expression is almost the exact same. Like it's equivalent mathematically. Does this look a little bit nicer? Pretty. Okay. Now, let's just think this out one step further. We're not dealing with rational functions. If you have a graph, and imagine a graph in your head, the only place that it has a value of 0 is at its what? We only need the roots. So when we're solving these, we're going to do a couple things. I'm going to make first comment. If we know the roots, or give me another word I could use there instead. So careful. I like where your head's at. But if we know roots, or what's another thing that we can use for roots? There's 3 other words. X-intercepts. I hear whispers. Zeros. Solutions. Cool. If we know, and I just want to make sure that we have them, roots, this is easy. Now, Mickey, you said asymptotes a second ago, which only because we're dealing with strictly polynomials, we don't care about the asymptotes because there won't be any. When we make the jump to rational, we'll see same idea applies. Now, we're going to go over just a little bit of language to work this out. Here we go. First little piece. I'm going to define for us, because we're going to keep talking about this, the related function. And then we're going to use all this vocab and see that you guys have already done a bunch of these. The related function for an inequality like this, instead of having greater than or equal to 0, which is nicer than greater than or equal to negative 2, just for the record, but instead of inequalities, it'd be so nice if I just had equals there, right? So all we need to do is the related function when 0 is isolated. Or we could say variables, it's either one, isolated, replace 0 with f of x, and we're going to replace this, and I just don't want to write it, and I'm not going to write all the variations just so you guys know, these things, the inequalities themselves, with equals. In doing so, just so we can see it, and I'm not going to write it down in this particular example because we'll do it here in a second, this right now is an inequality. If I wanted to change this piece right here, this nonlinear inequality, and I asked what's its related function, what are you going to replace the inequality with? Equal, and what are you going to replace the 0 with? F of x. Now, whether or not we actually write f of x, we'll see if we need it, but I want that conceptual idea there. We have a related function. Now, there's only a few places, and I'm going to sneak this in, and it won't apply all of it to polynomials, but we are also going to discuss what we call the key numbers. And that should be vocab as well, so I'll go ahead and cap it. Okay. We're going to do two versions. Most of you guys typically write down word for word what I write down. I want to stress, as always, it's up to you. I try my very best not to write down more than we need, but it might be more than some people need from time to time. Key numbers. The first way, and this is what you can elect if you're going to write down, the places, or the points, if you'd rather, that a function, or the function in this example, changes signs. And I'm going to say may change signs. Now, this is the wordy version. We're going to hit it again. The points that a function may change signs. Those are my key numbers. Charles, only 2 places that we know of at this point where functions can change signs. What's one of them? The roots, love it. And Kalisha, what's the other one? Good. Roots, and what sort of asymptote? So, they're the zeros of the denominator, which let me see if I can word this question differently. Are they vertical asymptotes, horizontal, or slant? Good. Vertical asymptotes. These are my key numbers every time. Now, it turns out that to deal with these, super duper easy, we're going to use one more vocab, and then you'll see that we've actually been doing these problems all along. All I need to do is determine, and will you do this, our test intervals. Now, this is the first time we've seen this word, or these words together, like, I don't know how to word that. We've never written test intervals. Have we been talking about intervals on our graphs that have served importance? And then we test a number in those? This is our number line. And then I'm trying to think of the easiest way. Can I say, you can write the number line we've been using. I'm fine with that. Alternatively, the number line with key numbers, which are just going to be our asymptotes or zeros, and sign of test point, or of test value. Okay. Our intervals are the things that we've been doing every time to graph these, because I knew where this was going. I have, hopefully not in a bad way, cut out a lot of work when we sketch graphs instead of like taking the time to actually do the points and stuff, because we get pretty much the main story, or most of the story, just by sketching them. A better graph would be more precise if we're looking at it and using it to like actually make predictions, but the sketches are sufficient for our purposes in here. Okay, we're done. Which means we're just going to try one of these, and we'll see if we can't work out a set of steps. Let's continue that problem that we started earlier. So right here, and then we'll look at another one in a moment. Okay, before we continue on, any part of this that you look at and go, oh, I don't like it, I don't get it, I don't understand. Let me rephrase that. What parts prior to graphing were you struggling the most with in a previous section? Can everybody find the zeros and asymptotes? roots. Can you put those in order on a number line? We will. I guarantee you can put them in order on a number line. We're going to do it right now. Let's check it out. So we're going to make this. You want to do the exact same problem we had above, or do you want to do a different one, harder one? All right. So I'm just going to say solve inequality, which for anybody who is out, inequa. I just don't finish the word. That's the only thing in math that I know of that's going to look like this. We're going to solve an inequality, and I'm just going to copy this one. I want us to determine when is x squared plus 3x greater than or equal to negative 2. That'll be our first one. X squared plus 3x greater than or equal to negative 2. All right. Greater than or equal to negative 2 is okay, but what's more fun or easier than greater than or equal to negative 2? 0. Can we make that say greater than or equal to 0? Let's do it. I'm going to add 2 to each side. So this is that whole isolating the 0 or isolating one side of the equation. Isolating 0 sounds weird, but it's what we're doing. If I add 2 to each side, everybody cool with this is the first little thing. Now, this next comment, I would encourage you guys to write on every problem. Greater than or equal to 0 literally means positive or negative? Positive. I am not going to require it, but I would suggest every time when you start a problem like this, one, you should always write down the original, like the way it's written. Step 2, once you get it to be 0, make sure you notice it's positive or not. Okay, beyond this, we're now going to find the related equation. And you won't have to write this every single time, but this can be hard to think about. I'm going to replace a 0 with a what? So we are really considering f of x, and this inequality gets replaced with a what? Equals. This is my related equation. Excuse me. Okay, nothing crazy has happened. This just makes it a little bit easier to connect this idea to the graph, which we don't really have to graph them. I'm not really going to graph them, but we could. Okay, right now we have a polynomial, something with nice integer powers and no imaginary pieces. No fractions and x's in the denominator, like this is as nice of a function as we can get. If this sign was going to change from positive to negative or vice versa, it could happen where? Louder. At the roots. Can we find the roots? Let's find the roots. Now this is where it's going to feel silly. To find the roots right away, what am I going to replace f of x with again? 0. So I'm just going to make a little note here. I'm going to say find roots. And we're going to factor this guy to do that. Now, in my mind, I always like to have the expression on the left. If you want to have the 0 on the left instead, I'm fine with it. Doesn't matter to me. Okay. I want you guys to factor this for me real quick. So I see everybody doing this. X plus 2 and x plus 1. Okay, which means what are the roots? Or in this case, I can call them roots, or up above we define something else. Key numbers. They're the same thing in this particular problem. Okay, what are the roots or the key numbers? So I'm going to write these as roots, and we'll talk about why, because that idea of multiplicity is going to kick in here also. Okay, I have roots at x equals negative 2 and negative 1. Are there any asymptotes? Is there any chance that I'm going to pick an x that makes me divide by 0? Never. There's no x's in the denominator. So check it out. There's no key numbers. I'm not going to write them down, but each of those roots showed up how many times? Once, which means I know for a fact that on either side of the root, it's going to change sign from positive to negative or vice versa. If it had shown up twice, it'll be the same on both sides once we do our interval. So here we go. What two numbers did we find that need to go on this graph? Negative 2 and negative 1. The biggest piece that people make silly mistakes with, make sure they're in order. Most negative to the left, most positive to the right. because if you get them goofed up and you're trying to use multiplicity, it's going to get wonky. Okay, now because these are roots, there's nothing crazy we have to do. Can anybody pick an interval to test? So let me rephrase that. We have 3 intervals, I think. And that was just poor language of my choice. We have everything over here, that's one interval, everything forever that way. We have another one in the middle, and we have another one over here that's everything to the right forever. 3 distinct pieces, right? Okay, I don't care which one we start in. I know where I would start. I need a number, any number that's not -2 or -1. 0 is the choice that I would go with because that's in the easiest interval right in the middle. Check it out. I'm going to use this as my test point or my test value. When I... Go ahead. Oh, it's not in there. Look at me making mistakes on purpose in front of everybody so that you catch it. Cool. All right. Scratch that. I'm going to plug it in here. If I plug in a 0, thanks for the catch, guys. Now, notice, this is my original function, and I've written it down. I can plug it in here pretty easily. Alternatively, though, just remember that this is equivalent. This is just the factored form and the expanded form. The same thing. It doesn't matter if we plug in here or here, we're going to get the same value. Which one would you plug into? Top or bottom? The factored one? Okay, so let's do it. What's 0 plus 2? 2 times what's 0 plus 1? So 2 times 1 is... Now, it turns out I don't care about the number even a little bit. Because all I care about is whether it's greater than or equal to 0 in the end. Did we just get a positive or a negative? Positive. Guaranteed. It wound up to be a positive 2, which on the graphing, if you wanted a real specific thing, I know it's the 0.02 is what we just got out of it. Have I lost anybody there? Okay. If we had to pick a test point here, what would you choose in this middle interval? Negative 1.5, Angel silently mouthed confidently. All right, looking at it, I don't care about the number, but let's check. Negative 1.5 plus 2 would be a positive or a negative? It'd be positive, right? Because it's the same as doing 2 minus 1.5. So that would have been a positive. Don't care what the number is. What about here? Negative 1.5 plus 1. So that'd be a negative. Which, if we had used multiplicity, if it was positive here, it better change. But we just verified it's a negative here. What do you think it's going to be over here? Convince me without using numbers. Multiplicity is an odd number 1, right? Okay. At this point, we're almost done. You guys don't have the ability to shade these things. You are going to be asked to graph these, and I do it a little bit different than your book, just so you're aware. Looking at it, hate the way your book does it. Really hate the way your book does it. I was looking at the very beginning, and this is why I write it. I'm looking for where it's what? Positive. So, a little bit of a throwback. I'm going to graph it just on this number line, just so you guys are aware, and then we'll write our answer as well. Which intervals is it positive in? Left, middle, or right? Left and right. So check it out. Your book is going to present it slightly differently, just so you're aware. Is it open circle or closed? How do you know that? Okay, so the way that I do it is above the line, I would do a closed point. And then if I want to go positive from there, do I go left or right? I go left. Now, there's half of my graph. Over here, at -1, is where it changes again. Closed point or open point? Closed again. And this pushes which direction from here? To the right. This is the graph of our inequality. Now, we could graph it on the actual thing and see that, oh, yep, this is a parabola that has its vertex somewhere in here, and then it rises above. Alternatively, we've answered the question entirely. One more little thing to do. Do you guys recall these two notations? Set builder and interval notation. I bet you will, but we'll check it. We are working with which variable in this? X. Now, do you agree that the numbers that make this inequality true, there's infinitely many of them. Because there's infinitely many numbers over here, and there's infinitely many numbers over here. We can't write them all. So we need a way to deal with. If we're looking at a set, and you can use either of these, this is a set of all x such that one of two things is true. I know that x has to be less than or equal to which number? X is less than or equal to -2. Or what's the other option that gives me answers that actually work? X is greater than or equal to -1. This is set builder notation. I like this one. It makes me feel fancy when I write it. There's an alternative notation that if you guys prefer it, I'm totally cool with it. And I'm going to show you what I don't like about what your book does. When your book graphs these, and you will never see me do it this way, just so you're aware. But when your book graphs these, I'm going to make it bold. They use slightly different notation. They use a bracket to indicate, and I hate that color, I'm going to use white. They use a bracket to indicate that, yep, we touched this point, and then they just bold it over the line. And it's all fine and dandy if you have like editing software, but that's hard for me to read on a number line, and I imagine it's kind of hard for you to read on a number line with pencil. These two things mean the same thing. Bracket means I include it, and I go that far. Now, the interval notation you guys are probably going to like more, just realistically. We start how far to the left, and we're just going to work our way right. How far to the left do you start on either of these graphs? Negative, careful, further left. Negative infinity, because we have to go all the way over to where it starts, which it doesn't, right? It's just always positive. So check it out. We start at negative infinity, and everything's fine and dandy, and we keep working up until we get to which x value? -2. Now, here's where interval is rough sometimes. Do I touch -2? It was or equal to, so I'm going to include it. I'm going to use a bracket right here. Now, do you ever touch negative infinity? Can't touch it, right? It's like we'll never get there. Anybody recall what I used to indicate I don't touch it? A parenthesis. Now, we'll see this again because we'll do another one. Parentheses indicate we don't touch. It's just like the open circle. Brackets, we do touch. It's just like the closed circle. Okay, now, there's a whole nother part of our answer because there's only half of it, right? We tie things together. Like marriage sometimes is called a something between two people. There's a lot of words that we might expect. You guys ever heard of union? Check it out. We're going to tie or marry these two sets together with a union. It's not a U, it's just it's a U without a tail. We're going to union this. This is our or statement. Where do we start back up? So I've knocked out all this so far. We start back up, and I'm just working left to right. What's the next number that we're going to hit? Do I include it? So what should I put here? We will bracket. And how far to the right do I keep going? Can you ever touch positive infinity? How do I indicate I don't touch it? We're done. Okay, this sounds fake and stupid. For real. There's something called closed sets. You include both ends. There's things called open sets where you don't touch either. It'd be parentheses on both sides. Guess in the dark. Like make up the dumbest word that you can for one that's open and closed. So, clopen. 100%. Clopen is the word that's like legitimately used. Okay. Does this feel like we're doing anything different than yesterday? So straight up, exactly what we did yesterday minus the graph. Next year, maybe I'll switch these sections because I think it makes sense to switch them. Now, if you want verification, I can pull this up on Desmos, but I guarantee what we're going to see, and don't draw this, is, let's see, 0 would live like here, right? Roughly? What you're going to see is a parabola that does this. It's positive. It goes below the axis here, and it comes above the axis again. We're graphing it without the y-axis is all that we're doing. Cool. Let's kick it up a notch. Because I don't know that I really need to go crazy into it. Oh, yep. I really want to finish this. I want you guys to try one for me. Okay. This one. You think PQ could show up? Probably. I'm not going to say it does show up here because I want you to talk it out with your groups. But I want to see how you go with one more real quick. And let's check it. I want you to solve with your group 2x cubed minus, lost my spot, 3x squared minus 32x. Ow. I'm messing with you. Let's say is less than negative 48. And that's an obnoxiously large less than sign. So I'm going to fix that because it's going to annoy me. Cool. Find your related equation. Find its roots. Put them on a number line. I'm going to give you guys a head start.